Hi everyone, Tina here, and today I'd like to talk about proof. Specifically in this video, I want to talk about methods of proof you'll need to be comfortable with during your first year of your A-level maths course. I've made videos on proof at GCSE level, so I'd recommend you watch these if you haven't already. I'll go through an overview of the methods first, and then we'll take a look at some examples. Here are the three methods of proof we need to be comfortable with in year one. We've got proof by deduction, proof by exhaustion, and disproof by counterexample. Starting with proof by deduction, that's when you start with some known facts or definitions and then use logic or algebra to reach the desired conclusion. With proof by exhaustion, you're going to break the statement down into smaller cases and then prove each case separately. And then for the disproof by counterexample, you just need to provide one example that does not work for the statement to prove that it is not true. I'll go through two examples of each type. Example 1, proof by deduction. Prove that the sum of the squares of two consecutive odd integers is always 2 more than a multiple of 8. So we need to start with some known facts here. Specifically, we have two consecutive odd integers, which we can represent in algebra as 2n plus 1 and 2n plus 3. It then talks about the sum of the squares of these. So that means we want to square them both and add them. And then it's a case of just following the algebra through. So we want to expand both of these brackets. Do this however you like, but I'm using FOIL. We can then simplify and we get 8n squared plus 16n plus 10. And at this point, I'd refer back to the question. We want to prove that that expression is always 2 more than a multiple of 8. To do this, we can take out a factor of 8. And if we do it this way, you can see that if we expanded that, we would get 8n squared plus 16n plus 8 means we need to have an extra plus 2 on the end. This is 2 more than a multiple of 8 because 8 times anything is a multiple of 8 and then we're adding 2 on the end. Example 2, prove that n squared plus 7n plus 15 is greater than n plus 3 is true for all values of n. For something like this, I'd recommend we pull all the terms onto the left so that we can end up with a quadratic being greater than 0. This is because it's easier to work with quadratics. We know what we can do with them. For example, we can take this expression and complete the square. Now, the reason I've done this is because completed square form tells us the coordinates of the minimum or maximum point. And in this case, we've got a minimum point with coordinates -3, 3. If we were to draw this on a sketch, -3, 3 could go there somewhere. The quadratic would then look like this. The fact that the entire graph is floating above the x-axis or n-axis in this case shows that no matter what, the entire quadratic expression is always going to be greater than 0. For any proof question though, you want to write a couple of statements at the end. So you could say something like, therefore, or this implies that n plus 3 squared plus 3 is always greater than 0 for all values of n. And therefore, the original statement is also true because this was just a rearranged version of this. Example 3 is an example of proof by exhaustion. Prove that n squared plus n plus 11 is prime for all integers between 1 and 5. Now, we said that proof by exhaustion was all about breaking the statement down into smaller cases and proving each case separately. In this case, we want to investigate each integer between 1 and 5. So let's say we've got n equals 1. If we sub 1 in to the expression, that gives us 13, and that's prime. If we sub 2 in, we get 17, which is also prime. N equals 3, same thing again, but using 3 instead. That gives 23, which is prime. N equals 4, 31, also prime. And then you hope that the last case is also prime, but we'll check, equals 41 prime. Implies, or therefore, statement is proved. Example 4, prove that for any integer x, f of x, which is x cubed plus x plus 1, is odd. Now, in this case, we're not given specific values of x that we need to test or prove. We're just asked to prove that it's true for any integer x. You can still do a proof by exhaustion here, though, because you can break the statement down into two cases for x. Case 1, x could be even. In case 2, x is odd. If we prove the statement for both of those cases, we will in fact prove that it's true for any integer x because any integer x is either going to be even or odd. Let's start with case 1. So if x is even, we can say something like let x be equal to 2n. We can then sub that into the expression and expand it. Now remember, we want to show that this is odd. So to do that, we can take out a factor of 2 and then leave our plus 1 on the outside. This is enough to say that this is odd because we've got 2 times anything, which will be even, and then if we add 1 to it, makes it odd. Case 2, x is odd, so we can say something like let x be equal to 2n plus 1. Again, we're going to sub that in to our expression or function. In this case, the algebra is a little bit more involved, so I'd probably be tempted to take this cubic and expand it out on the side somewhere. So if we do that up here, 2n plus 1 cubed means 2n plus 1 3 times. Different people expand this differently, but I like to expand the second two brackets first and then incorporate the first bracket. So that would be 8n cubed plus 8n squared plus 2n plus 4n squared plus 4n plus 1. Simplifying gives 8n cubed plus 12n squared plus 6n plus 1. We can then take that expression and sub it into our proof. So now we can say that this is equal to 8n cubed plus 12n squared plus 6n plus 1 plus the 2n plus 1 plus 1. Simplifying, we get this. And again, we want to show that this is odd, so we'll do the same trick, pull out a 2 and make sure we have a plus 1 on the end. Again, this shows that this is odd. 2 times anything plus 1 is odd. Therefore, or this implies that the statement is proved. Moving on to disproof by counterexample now. So example 5 says that prove that x plus y, all in brackets squared, is not equal to x squared plus y squared. Now, as soon as you see something like not equal to, you can consider doing a disproof by counterexample. That means we just need to come up with one example that shows that the statement is not true. For example, we might choose x to be 2 and y to be 3. If we sub that into each side, so x plus y all squared would be the same as 2 plus 3 all squared, 5 squared, 25. On the other side, x squared plus y squared would be 2 squared plus 3 squared, 4 plus 9, 13. And 25 is not equal to 13, therefore statement is proved. Last example, disprove the statement n squared minus n plus 3 is prime for all values of n. Again, that word disprove makes me think of disproof by counterexample. So can we think of one example to show that the statement is false? At this point, trial and error is the way to go. So you might want to start small. Let's say n is 1. Sub that in, see what you get. That gives 3, which unfortunately is prime. So it means we need to look for another example. Let n equals 2, 5, prime. N equals 3, 9, not prime. And there is our one counterexample. Therefore, statement is disproved. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else that you think might find it helpful. Thanks, and see you next time.